So our next speaker is Jiaqi Liu. She's tech lead at Button and director of Women Who Code New York. She'll be talking about building data pipelines with monitoring and observability.
Hello, good afternoon. Thank you for that wonderful introduction. I'm very excited to be here today to talk about building data pipelines. And one of my favorite topics on building data pipelines is building them in such a way that you know what's going on under the hood. So I'm very excited to give this talk. A little bit about myself and the company that I work for. I work for a tech startup called Button in New York City. We are roughly 130 people. And as a company, we are focused on building out a e-commerce platform on mobile. So we are building out a marketplace such that we can connect apps that are looking to increase revenue with other apps that are looking to drive more commerce sales through their own apps. And the part that I work on is I work on the data pipeline that takes in various purchase data from our users and converts them and calculates commission for the appropriate advertisers so that we know who to attribute it to and how much commission to pay out. Today I'll be discussing in conjunction with my work, but also how data pipelines behave overall. And the overall agenda is that I'll be talking about data pipelines and ETL jobs and the challenges associated with monitoring them and testing them. And then some of the key features around how to overcome those challenges. And finally, we'll talk about a full-fledged test suite and monitoring stack. So very briefly on data pipelines. So at its core, there's this concept called ETL. A lot of you might be already very much familiar with it. It sounds very simple. There's usually an extract step where you have to pull data in some way to get that data out. There is a transformation step where you are running some sort of analysis or transforming the data in some way. And then there's lastly a load step where you're persisting the data or you are loading it into some sort of visualization tool. So that's kind of the general framework, and a lot of data engineering is built around it. But this isn't quite it. These are the steps it takes for data to get from one place to another, but it doesn't really sum up the overall challenges of working with that data and making sure that once the data is loaded into your database, it's actually usable. So to quickly iterate, a quick example, I was recently at a conference in Portland called OzCon, and before I attended, I sort of went and pulled a lot of their data from their website of all the talks that they had, and then transformed it so that it is serialized and fits some sort of JSON structure. So the first step, pulling the data from their website, is a extraction, and then transforming it into the structure is actually already part of the transform step. And then I try to do some more on parsing the specific speaker information, so an additional layer of serialization and transformation. And I stored all of these talks into a list so that I can randomly select the talk to go to if I didn't know what I wanted to check out. And then next I saved everything to a CSV step, which sort of is the load step in this example where I'm persisting the data to storage. At a very high level, this is sort of what the data pipeline looks like. There is a source, which is the website. There's structured HTML that's converted into some sort of serialized JSON. The select random talk could be considered some sort of algorithm. And then writing to file persists it, so that's the final load step. It sounds very easy, and it's not a lot of steps, and it's pretty easy for me to verify if this was successful. If I don't have any data after I try to parse the HTML, then something is wrong with the parser. But in reality, production data pipelines are never quite as simple. So this is an actual example of a data pipeline that I work with. At Button, because we work with so many different partners and so many different brands, we see a wide range of data at each step. And in even the extract phase, there's this fan out of different options that you could have, which makes the data processing a lot more complex. The other challenge that I work with is that sometimes you get data in batch format. For instance, when I went and pulled all the talks from the OSCON website, that is a batch together, a complete set of data. But sometimes you get processes streamed in. So you'll get an event stream where you have one event at a time. And these tend to have very different SLAs, service level requirements, and require different monitoring strategies. And it's very tricky to actually have a pipeline that merges batch and stream data processes. We'll touch on that a little bit in the talk. There are quite a lot of really helpful tools out there, both open source and provided by cloud services, that are really great for orchestrating your pipeline. This talk won't really focus on those tools, but I wanted to make sure that I bring it to your attention, especially on any kind of data pipelining talk. It's kind of hard to avoid talking about orchestration tools. A lot of the topics that we talk about today, like monitoring and scheduling, some of these orchestration tools will automatically do for you. Like Airflow, for instance, will be able to alert you if your job doesn't complete. Airflow and Lineage are both open source tools, and they operate in a way where they structure your data processing into DAGs so that you can move from one step to another. And AWS Data Pipeline and Google Data Flow are provided by those respective cloud providers. And each of them have really unique features that might make it useful for your particular use case, but that is not quite covered in this talk. That would be, it's almost worth a separate talk on its own. So you've seen a couple of data pipelining examples. Let's go over what could possibly go wrong. So there's quite a lot of issues that could happen. So in a batch job, you could actually, your system, whatever's orchestrating it, might fail to schedule it. The most obvious and easy way to verify is probably just to check if it's finished after an expected amount of time. Your batch job could have started, but it took too long to run, or it ran out of memory when it's running, so never successfully completed. So your data could be corrupt or malformed in such a way that you didn't get that output you expected. In a stream processing event, your stream could get backed up. Your data could be dropped or lost. One real case example that we've seen was there was a lot of events going to our database, and each of them were locking the table in order to create a transaction and store that into the database. But because there were so many concurrent locks on the database, you could have a database that lock, in which case your stream would then get backed up because nobody can talk to the database anymore. If you're working with a non-deterministic system, so any kind of machine learning system, you could have a lot of trouble monitoring it because your expected outcome isn't as easy to predict. So for example, how do you monitor and look at the success of a batch job? So this is a real visualization of time series data for a batch job. The spikes represent the number of data points being created here. And you can see that this graph is very spiky. So there's some peaks at certain times, hopefully in regular intervals, and then it sort of just dies down and flatlines when the job isn't running. So being able to visualize this and then being able to assess what level of, one, how big are the maximum spikes so that you can adjust for things like memory and CPU for the system, and then also what are your expectations over time so you can alert on this data. Stream processing is a lot more different. In a way, it's actually very exciting because there's a lot more metrics that you can capture to monitor it. So things like ingress and egress of the queue, so number of messages coming in, or number of events coming in, and number of messages going out. Ideally, those things are equal, and ideally, you're following it at a pace that makes sense. So things like latency, you want to be able to read messages from the queue in a consistent and reliable way, so you don't want the queue to start building up too quickly. And then last but not least, age of the oldest data point yet to be processed. So you could have a queue where you have data processing, but there is one constant data point that's getting either rejected by the processor or isn't actually getting processed. So you might have low latency overall, but you have some malformed data point, and you want to be able to check for that by calculating the age of the oldest data point that has yet to be processed. So a lot of concerns. You want to worry about specifically data processing and the speed required for that, but also data integrity. So you want to validate that your output is correct, and you also want to know that your pipeline is running in a timely manner. So kind of on that note, it's not just about low latency. You could always have your job running successfully, but not actually be getting the results that you're expecting, or you could be getting false results that you're driving, I don't know, business decisions or analytics decisions on top of. So in my previous demo, what if the website completely changes, and I assume that certain HTML tags were being used for certain fields, and that was how I was parsing the data. If that changed in any way, my script would break, and I could potentially be populating a field with a different data set that I didn't mean to have for that field. So you just kind of have to know what parts of your, what are some failure points for your data pipeline. So this sort of brings me to my overall message, which is that data pipelines need to support interpretability and observability, which are both kind of big words and maybe a little bit buzzwordy, but I'm going to talk a little bit about what they mean. Okay, so interpretability is a term for data science, and you want to not just understand what a model predicted, but why it predicted it, and then also build in guardrails so that you can allow for debugging, editing machine learning models. So there's a couple of concepts associated with it. So fairness, for instance, you want to make sure that the predictions that your models are making are unbiased. A good example of this is that an interpretable model should be able to tell you if it's decided against whether someone is creditworthy or not for, say you're applying for a credit card, and they should tell you that that judgment is not based on, say, racial bias or some other form that is technically, illegal, at least in the United States. This is very challenging, especially if you have a lot of features in your data pipeline or your model specifically, and you don't really know exactly what feature might have implicitly or explicitly introduced bias in your system. You care about privacy. You want to make sure that your model doesn't expose sensitive data that is protected. You care about reliability, or otherwise known as robustness, that you want to test that a small change in the output doesn't lead to a big change in the outcome. So tweaking a small parameter shouldn't lead to a drastic change in your output set. Causality is another factor, which is you want to check for relationships that are cause-based instead of relationships that are correlated. So you should be a predicted change should actually happen in reality, not just in the data set. And then last but not least, trust. So this is one of the reasons why interpretable models are very important, because it's much easier to trust something that you can understand, that you know why decisions are made a certain way, than actual black box. Because Button is a marketplace, we observe the output of a user's behavior, but we don't necessarily know what the user is thinking. So if they've increased purchase right before the holidays, we assume that it's because it's due to holiday shopping. But it could be, it could very well be this merchant is running a promotion and has a lot of sales going on. It could be there is a lot of demand for a particular inventory because it's very popular that year. So being able to tie the data to actual user behavior is very interesting and very important. And there's a notion that part of data science is a lot of behavioral economics and behavioral science too. So observability, unlike interpretability, which is a data science term, observability comes from the SRE world. So SRE stands for Site Reliability Engineers, so it comes from DevOps and deploying systems and monitoring them and maintaining large ecosystems. So you can't really catch for things that you don't know about. That's kind of the notion of like being a DevOps engineer or SRE, is that you can only really alert on things that you can predict. And then but because you can't catch for everything, you want to enable yourself to focus on debugging. It is, to me, it's kind of like the SRE version of interpretability. This diagram comes from Cindy Sudharan's blog on monitoring and observability, which is a really helpful read if you can get to it. But everything covered here, both testing and monitoring, is on the side of your best effort to understand the system and monitor for correctness. Unfortunately, you can't cover everything, so anything outside of your best effort and your known abilities to understand the system falls into the realm of observability, meaning that you want to provide yourself with the tools to be able to diagnose the issue should something happen outside of your expected failure cases. And you don't have to try to outline every failure case possible. And you do that by building in tools so that you can debug your system and building in metrics and logging so that you can capture data that you might not alert on but might be helpful to you later. Cool. So at work, we have a model called mystery-free prod, which means that whatever happens on production should be something that we understand. So even if we have a bug and it magically fixed itself, that's still a mystery if it's unknown why it went away. So we want to be able to explain why any changes are happening in production. So that's sort of the notion of having these two things, both interpretability and observability, is that you should understand what your production system is doing and be able to explain why it's doing what it's doing. Cool, so we'll talk now about pipeline features that support these two concepts. At a high level, there's 3 features that I always advocate for. One is immutable data, and then being able to trace data lineage, and lastly, having some sort of test run feature so that you can evaluate before persisting the data. So immutable data is sort of core to designing a system that is idempotent and reproducible. Idempotency means that the same output will consistently produce the same output. So whatever your transformation is, there's no additional side effects. And you want your system to be reproducible because if something goes wrong or if your output is unexpected, you want to understand, you want to be able to run that again and verify that that consistent behavior is happening and be able to test that outside of a production environment. An example of immutable data is with bank transactions. So in this paradigm, data is stored as an immutable sequence of events. So you might have a credit, which is sort of a deposit into your account, and then you have debits that sum up. The alternative to this view of storing data and modeling data is if you just always overwrite it with the current balance, which might be sufficient to your use case if all you want to do is show the user their current balance, but it makes it really hard to construct the history of the event that led to that current balance. So if you're calculating it wrong, it's a lot harder to figure out why. So data lineage is another concept that I'm very excited about. It means that you can sort of trace where your data comes from. So immutable data usually allows you to create data lineage. So in that previous example, because every event had a timestamp, if we go back and look at if there's something wrong with calculating the total balance, you can go back and look at that table and trace that, oh, maybe we dropped an event, or maybe we double counted an event. So one aspect of, I guess, functional programming is that an incremental process is idempotent. So let's say your data is immutable, you have some sort of idempotent process, but you can actually build additional ones in order to construct your end pipeline. You want then to be able to go back and find out what the source, what the inputs to your next steps are, so that you can identify and narrow down to exactly where something might have gone wrong. So in short, I did this doodle by myself, by the way, and data lineage is basically like version control for your data. In the same way that you want version control for your code, you kind of want to know what version of the data along with what transformation led to a particular outcome. If you have to revert that transformation, if you have really good lineage constructed, you should know how to reverse that transformation so that you can go back to what you had previous. So a couple of ways to do this. You can tag records with metadata. So something that my team and I have done is we've tagged some of our transformation steps with the git shard of the code that ran it, and then the file that was the input to that data set. You can log to a distributed tracer. So tagging with metadata is viable if you have the data space in your production database to do so, and it's something that you might want to query on top of, but you might not want to add all this extra data into your production data store. So you can actually log to a separate distributed tracer. So it's something like Elasticsearch on top of like Kibana, and tag those with the appropriate record numbers so that you can trace back to what caused what output. So last but not least, I advocated in favor of a feature called having a test run, which means that you should be able to test on some sort of real data, not just a QA data, before handing it out there to be exposed to the world. So the sort of, I guess, the analogy to web development is that a RESTful API will very quickly respond with an error code if you're trying to send it some sort of data that isn't expected, that it doesn't know how to work with. But a data pipeline is a lot longer of a process, and that feedback loop is a lot longer sometimes. So you might be in a position where you don't get the signal that something's wrong with this data until you reach the very end of your data pipeline. So you kind of want gradual and optional validation along the way, so that you can document your assumptions and encode them. And to do this, one of the easier ways is that if you could test outside of the production environment on real data set. Okay, so this goes back to what assumptions did you make about your data, and that ties into your data validation framework that you might want to be building out. So in data science, you want to know about the contextual assumptions of the data, where it came from, any kind of behavioral assumptions that you may have made. And then when it comes to data engineering, you have to document the numerical and data type assumptions. So a certain field must be greater than 0, whether a field is a string or an array or a number. It takes evidence to differentiate valid assumptions from invalid ones. And so it might not always make sense to have strict validation right at the front door. There is, of course, some non-negotiables like security or privacy concerns. You don't want data to come in and corrupt your database. And then as you build up your domain expertise, you should be able to actually build in additional data validations. So one example I have for this is being able to define an actual schema and allow for changes in the schema and evolution of the data. So in this schema, I kind of assume that a talk and a speaker has a one-to-one relationship. And I kind of assume that there's no maximum number of fields. I can have as many characters as I need in the schema, and that could be persisted. So a good way to define schemas are with any kind of data serializers, but in particular, I am most familiar with protocol buffers, which are also known as protobufs, and they're a language agnostic way to define schemas and to serialize data. So it's a tool produced by Google, and it is kind of similar to XML, but it's a lot more robust and a lot more easier to work with, also a lot lighter. And they're language agnostic, which is really good for especially working in a microservices setting where you might have code in different languages. So this is kind of an example of what a protobuf looks like. There are, again, different field types that you're defining, and those are then validated against the data. You might need to know that some fields are required versus some fields are not, and then you might want to constrain certain fields instead of freeform that they're enumerated by the types that are allowed. All right, so when capturing the pieces of data that introduce uncertainty to the system, you can't always determine the correct behavior. So validation also evolves as the data evolves, and having this gradual testing in the QA environment allows you to grow it in the right way. This is actually particularly helpful in one example of creating backfills. So something my team and I have run into in the past is, let's say that your assumptions were incorrect in production. You can't always have everything validated in the sense that you can't predict what you don't know. And in order to correct that behavior, you want to backfill the production data with the correct code. So being able to, one, have the correct assumptions in place in your business logic, to being able to then test those assumptions across a longer period of time and against historical data, and then actually persist that into the database itself. So let's talk a little bit more about testing the code and the logic associated with that. Okay, so this is from Martin Fowler's blog, and this is known as the test period, which was developed by Mike Cohn. At the core layer, you have these unit tests, which are foundationally trying to test the specific functions that you might be writing or the specific steps in your data pipeline. Then you have service level tests, and then you get up through the pyramid, and you might have full-fledged UI tests if you're working with an app that a certain behavior from the user produces a certain expected outcome. So kind of similar categorization of tests. So you definitely want to have unit tests. You might also want to do, in addition to the more functional tests and the system-wide tests, you might also want to have regression tests to test that whatever you're shipping is better performing than what was there before. So for example, a unit test will just test one specific function. This function will retry. So it's a retry function, and will retry X amount of times, and then throw an exception after that. So this test then makes sure that those retries are being carried out. Functional tests are a little bit more of a black box. You have less dependency on the code itself, but what you actually would do is you want to make sure that in a deterministic system, the data that comes in, you should be able to test that data that goes into the system is expected in a certain way when it comes out. So what you're testing for is, so you might put in a feature, like a fixture of a data test, and then if it's compare the output to what was expected versus what it was generated, and that determines success or failure. Regression tests. So that's to make sure that when you are testing, when you are shipping one feature, you don't inadvertently break another feature. And the concept in data science is actually a little bit unique in that there is something known as the champion challenger model. So it's this notion that you might be running two slightly different statistical models in production simultaneously. One is the champion, which is the model that is serving traffic to actual users. The other is the challenger, which is a new model that you might have developed. And then you want to measure precision and accuracy for both of those models and see which one is performing better. And you swap over to the challenger model if it's actually performing better. And the system tests are a little bit more black box. At Button, we actually hit our production API and check for both response time and expected output continuously on our production system. And it's a very realistic way of understanding that the system is up and available and it's producing accurate results in a timely manner. So it checks a lot of the boxes that we're talking about. And it's actually a great way to alert on system failure. It doesn't really tell you exactly what part of the pipeline might have failed, but it does tell you that something is wrong. And if we built in great monitoring practices, you should then be able to determine from there what might be wrong. So measure the health of the overall system, and usually it can be part of your continuous integration or continuous deployment processes too. So I like to compare testing and monitoring from a data pipeline perspective with web services. So if you're familiar with web services, typically you have some sort of health check endpoint, and you can persistently check it that it's returning a 200 status code. And if it's not, you can alert on that, or you can actually make sure that there's some sort of self-healing happening. For a data pipeline, especially a batch job, you can also periodically check, or you can also confirm that a job has completed and is successful. And that's sort of the equivalent of a health check. And then for the integration tests, as I described before, you could make a post request to endpoint and then make sure that you're getting the correct data back. In a data pipeline, you can ingest fake data into your system, and this might be something you do in a QA or staging area, and then check that the fake data made it through the pipeline and it has the expected output. And then latency in the web world is sort of the response time of your API, and for a data pipeline, it's the time it takes to complete. All right, so monitoring. So the tools that we leverage are Prometheus, which is a time series database, and Grafana, which comes with the Prometheus suite of products, which is used for visualization. So the graphs I showed earlier were generated from time series data from Prometheus and from Grafana as well. So there's other tools that are also open source, like StatsD, which is a data metrics aggregator. And then there is things like Nagios, which is checks for system health. So it'll return 0 or 1 on the system, and it's much more binary. And also things like Jenkins, which is used for continuous integration and continuous deployment, but can also run a suite of integration tests. Grafana dashboards are incredibly powerful. This is an example of a Grafana dashboard powering a Kubernetes cluster, and it'll track things like cluster memory usage, CPU, cluster health, and then it also has time series data on, in this case, network I/O. So Prometheus works really well for recording numeric time series, and it actually, I have a diagram that I also drew. It is able to fetch data from services. So long-running services will have an endpoint that gets exposed to the Prometheus server, which scrapes that endpoint periodically. That could be every 10 seconds, every 15, every 30 seconds for metrics. And then it gets stored into Prometheus, the time series database for Prometheus. We use AWS, so there's also something called CloudWatch Exporter that exports CloudWatch data from AWS to Prometheus. And then there's this thing called the push gateway for jobs that might want to push data to Prometheus instead of being scraped. A good example of this is if you actually have a short-lived data pipeline and it's not long-running, it can't expose a port, then Prometheus can't scrape it. So you might want to be pushing data to Prometheus instead. It also has what's called Alert Manager. And what happens is the Prometheus server will evaluate these rules every so often. And these rules determine whether or not you want to alert on a metric. So if you configured a rule to say that I want the P99 latency for my server to always be less than 10 seconds, and that evaluates to be false, then it might alert, and then the alert manager will send notifications downstream to anything that you might have set up for it. There are four main metric types for Prometheus. One is the counter, which is always monotonically increasing. So a good example of this might be the number of errors your data pipeline has run into. The other one is a gauge, which is a single numerical value. So think of this as a temperature or current memory usage. And then the histogram and the summary are much more robust and can capture buckets of information, so observation, as well as quantiles. So the summary in particular will capture quantile, and it's really great for understanding quantile-based latency. So what I described about the 99 percentile latency for your system. I'm going to talk specifically about time series metrics that your batch job could generate. So for batch jobs, an important metric is knowing when was the last time it ran successfully. So you can put in, if you're working with Python, a snippet on both the duration to send to Prometheus or the time last success of the job. This will then allow you to build an alert that will tell you the last time a successful job has finished and whether or not it's in the expected range. And this allows you to set that threshold and alert on the system. For a individual data point, this is sort of an example where we are working with counters, and this data pipeline has processed all of these data points, and some of them were skipped, some of them have failed, and some of them were successfully processed. And it's really interesting to know what the acceptable threshold is, so where you see that spike of failed events or failed data points, that could be kind of weird versus maybe it's normal for us to have less than 10 failed data points per run. So it's important to gather these metrics so that when something happens, you can refer back to them and then build those assumptions into the system. Okay, so closing this out, for alerting, setting a threshold that works for you and going from there. Page on symptoms, so if you have to alert on something, alert on the symptoms, not the root causes, and then create a trail of causes so that you can properly diagnose. And then sort of the concluding thought is build your data pipeline with appropriate data lineage, immutable data, and a test run feature so that overall you want the ability to evolve your production system and make sure that it's maintainable. Thank you very much, and happy to take questions.
Thank you so much. Do we have any questions for Jiaqi?
Hello. I was wondering, could you clarify a bit more on alerting on symptoms versus root causes? Like, could you give some examples?
Sure. So the question was, can you clarify on alerting on symptoms instead of root causes. And if I can give any examples. So the notion here is there's probably an infinite amount of things that could possibly go wrong, but you don't actually want to be alerting all the time, because then you might fall into the habit of ignoring those alerts because they're so noisy. So something like a symptom would be, let's say your website is down, and the cause for that could be maybe one of your servers ran out of memory. So you want to actually page on the fact that maybe there's something that's trying your website every second or every millisecond, and it's not able to successfully get a ping on it. And then you want to make sure that somewhere you're tracking memory usage for your server so that you can trace that, oh, it has stopped responding because it's run out of memory or it's run out of CPU.
Quick question. What do you use for alerting? And as a data engineer, do you think that it's also equally as important for you to have like real-time, like an on-call incident response engineer on the team as well, or is that more for like the live production systems?
Sure. So the question was, what do you use for alerting? And then as a data engineer, is it important to have a on-call response, or is that more so for production systems? So for starters, so my team uses the Prometheus suite of products. So we also use Prometheus's own alert manager to trigger alerts. And we write alerts in the same regex format that I showed. That's actually not the best system because it is very threshold based and it's not very intelligent. So there are better systems out there like Datadog that will allow you to do anomaly detection on top of that and alert in a more intelligent way. We also use PagerDuty to actually page someone. That's an app on your phone that will constantly ping you if something goes wrong. For data engineering in particular, so it really depends on the system. We don't have an on-call rotation for batch jobs because they are very batchy anyway. They're already delayed, and you don't need to respond immediately if a batch job didn't finish. You can respond whenever you're in the office or whenever it becomes urgent. But for some of our production stream jobs, because those are serving user traffic and our partners would notice if they're not constantly serving traffic or there's significant delays in that traffic, that is somewhere where you have to page. So for us, it's very much business case focused rather than whether it's data engineering or software engineering.
Any more questions? No? Thank you so much, Jiaqi. This is a cute little plushie for you.
Oh, thank you so much.
Guys, well, I am running out of battery, so I'm gonna go and grab a cup of coffee. Why don't you provide us some feedback? We have been receiving almost no feedback. So please, the link is right there on the orange door. It's a bit.ly link.